So in this lesson, we're going to introduce you to what a limit is. And I'm sure in your calculus courses, your instructor explains it very formally, but we're just going to go with an intuitive definition here. And very simply, a limit is a value that the dependent variable approaches as the independent variable approaches a particular number. So let's look at one example here. Let's say we're looking at f of x equals x squared. So its graph will look, this is the x-axis, this is the y-axis. Excuse the messiness here, but hopefully you'll be able to see the idea. Okay. All right. So 1's on the graph because 1 squared is 1. Negative 1 is on the graph because negative 1 squared is 1. 4 is on the graph because 2 squared is 4. And negative 4 is on the graph because negative 2 squared is 4. So we'll have a parabola looking something like this. And as we get really close to x equals 2, f of x gets really close to 4. And that's approaching 2 from both below and above. Another example here. Let's look at g of x equals the square root of x. So we know 1's on the graph because the square root of 1 is 1. 0 is on the graph because the square root of 0 is 0. 4 2's on the graph because the square root of 4 is 2. And 9 3's on the graph because the square root of 9 is 3. So the graph is going to look something like that. And keep in mind, yeah, negative 3 squared also equals 9, but if you recall from algebra 1, we by convention take the positive square roots so that this thing can be a function, because if it, let's say if it went like this, it would fail the vertical line test. So for every value of x, you can only have one value of y, but ignore that there. Now let's say we approach 9 from both sides. We approached it from this side. You can see g of x gets really close to 3. Approached it from this side, you can also see that g of x gets really close to 3. And so we say the limit as x approaches 9 of g of x is 3. And here we'd say the limit as x approaches 2 of f of x is 4. So here we get really close to 2, x gets really close to 2, f of x gets really close to 4. In this example, when x gets really close to 9, f of x gets really close to 3. And the way we write that is, in this example, we say lim x arrow 2, so the limit as x approaches 2, or sometimes people say the limit as x tends to 2 of f of x, and this is also equal to the limit as x tends to 2 of x squared equals 4. So this limit is the value that the dependent variable approaches as the independent variable approaches 2. And that's exactly what I wrote up here. Okay, so bear that in mind. And so how do you think we'd say here that as x gets really close to 9, g of x gets really close to 3? Well, we'd say the limit lim as x tends to, so arrow 9 of g of x equals limit as x tends to 9 of the square root of x is equal to 3. Okay, so in these two examples that we just took a look at, this one and this one, you'll notice as we, like in this example, as we approached 2, as x approached 2 from both the left and the right, so coming from below and above, f of x approached the same number, 4. And here, as x approached 9 from both below and above, g of x approached 3. Approached or got closer and closer to or tended to, those, you'll hear all of those terms. But that doesn't always have to be the case, and we're going to look at an example where that's not the case. So say f of x is the greatest integer of x. And this function is a pretty cool function. You'll see it notated as int of x. Sometimes you'll see double bracket x. Sometimes you'll see it called floor of x. And sometimes you'll see a single bracket x. And what it basically does is you input any number and the function spits out the biggest integer that's smaller than the number that you inputted. And I know that's a mouthful, but let's say you inputted 2.2, so you wanted to find the int of 2.2. So we're looking at the biggest integer that's smaller than 2.2, so that's 2. Say you wanted to find the great int of negative 6.005. You're looking for the biggest integer that's still smaller than negative 6. And here, when I say smaller, I mean to the left of it on the number line. So if you see, here's the number line, 0, 1, 2, and so forth, and to the left. Negative 1, this is 0 here. Negative 2, -3, -4, -5, -6, -7, and so forth. So -3, -4, -5, -6, and -7. And you can see that -6.005 is going to be somewhere here really, really close to 6, but still to the left of it. This is going to be spitting out the value of the biggest integer that still lies to the left on the number line. So that would be -7 here. Because -6 is bigger than -6.005. As -7 is still less than -6.005, unless or to the left on the number line are equivalent terms. Okay, so how would this function look? I'm just going to draw it. I'm going to go ahead and draw the function and then explain to you why it looks the way it looks. Oops. Okay, so draw my axes here. Ooh, go ahead and erase that. Okay, let's pretend that's a straight line. Let's pretend this is a straight line too. Okay, this is 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Hopefully you can see that. -1, -2, -3, -4, -5. -1, -2, -3, -4, -5. Okay, so how does this function look? Well, I'm going to draw it here and then I'm going to explain it. And it basically continues like that. And it kind of looks like stair steps, and it's sometimes called a step function as well. But here you'll see, like, let's say we look at x equal to 0. The greatest integer. Oh, I made a mistake here. When I said the greatest integer that's smaller than the input number, it's really smaller than or equal to. So, int of 2 would be 2, not 1. Okay, so it's smaller than or equal to. Okay, so the greatest integer of 0, let's say you input 0 into this greatest integer function, so int of 0. Well, the greatest integer that's either equal to or smaller than 0 is 0, right? Well, let's say you looked at 0.5. The greatest integer that's either equal to or smaller than 0.5 is 0, so that's why 0.50 is a point on here. Let's say you looked at 0.999999. Okay, the biggest integer, greatest integer, that's smaller than 0.9999959 is 0, not 1. Okay, but let's say you went on the other side of, or let's say you looked at 1. The greatest integer that's either equal to 1 or smaller than 1 is 1 itself. You went on the other side of 1, the greatest integer that's equal to 1 or that's equal to 1.0001. Greatest integer that's either equal to 1.0001 or smaller than 1.0001 is 1. So that's why you see a filled circle. Open circle means the function's not defined where the circle is open, but it is defined where the circle is closed. Okay, so if f of x is int of x, and we're looking at f of 1, well, f of 1 is 1, not 0. So that's why you see a filled circle at 1, 1. But you look just to the right of it at 1.00001, just to the right of 1, 1. The greatest integer there is 1, right? That's why it's along this line. Let's say you looked at 1.5. Well, the greatest integer there is still 1. And it's still 1 even at 1.99999, but when you get to 2, the greatest integer becomes 2. So that's why you see an open circle here at 1, 2, but a filled circle at 2, 2. And looking on the side of negative x values, let's say we're looking at the greatest integer of negative 0.5. Remember, we're going to be looking at the biggest number that still lies to the left of negative 0.5 on this number line, and that's negative 1. So that's why at negative 0.5, the negative 0.5 falls on this stair step where y equals negative 1, y or f of x equals negative 1. At negative 1, the biggest integer that's equal to or smaller than negative 1 is negative 1 itself. Alright. And that's why you have a closed circle here for x equals negative 1 at negative 1 and an open circle at negative 2. But if you looked at negative 1.00001, the biggest integer that's smaller than negative 1.0001 or equal to it is negative 2. And remember, that's equivalent to the biggest integer that's to the left on the number line of negative 1.0001, which is negative 2. Alright, so you can see that negative 1.0001 falls on this y equals negative 2 stair step. Okay, so back to the idea of limits. Let's say we wanted to approach x equal to 1. We wanted to find the limit as x approaches 1. And let's say we looked at values closer and closer to 1, but coming from the left. So we were looking at 0.9999, 0.99999, and so forth. Well, f of x would be 0 there. Remember, the greatest integer is 0. But let's say we were approaching x equal to 1 from the right. So we're looking at 1.0001. The greatest integer there is 1. So the limit as x tends to 1. And when we're looking at limits from the left, we put a minus sign. That doesn't mean negative values. This simply means approaching 1 from the left of int of x equals 0. But the limit as x tends to 1 from the right, okay, this doesn't mean necessarily that we are looking at positive values of x. It just means that we are approaching 1 from the right, x equal to 1 from the right, of int of x equals 1. And to drive that point home, let's say we looked at the limit as we wanted to see the limit as x tended to -1 from the right. It's to -1 from the right. So remember, this plus does not mean positive values of x. It just means we're approaching this number from the right. So that means like values of -0.999999999. Well, and of the function we're looking at is int of x. So we input -0.99999, and int of x, what's it going to spit out? It's going to spit out -1. Alright, and but let's say we wanted to look at the limit as x tended to -1 from the left, okay, of int of x. Well, we're looking at values, say, -1.000001. The biggest integer that's smaller than or equal to -1.00001 is -2. So you'll notice here that the limits, this is an example of a function where the limits from the right, as you approach a value of x from the right and the left, are not necessarily equal. And they're not equal at the integers, but they are at non-integer numbers. For example, let's say we wanted to approach limit as, we wanted to approach 2.5, okay, from the right. Well, that limit is going to be 2, right? We looked at 2.5001. We'd get 2, but let's say we wanted to approach 2.5 from the left. So we'd be looking at x equals 2.4999999. Well, at int of that, like the greatest integer smaller than 2.49999, is still 2. So for some values, the left and right limits are equal, and for some they're not in this particular function. And this may have not shown up on the screen, but hopefully you got the point of what I was trying. Hopefully you got the point I was trying to make. Let me go ahead and erase some of this here. Or actually, this lesson's getting a bit long. In the next lesson, we'll look at another example where we'll see that the function doesn't even have to be defined in order for the limit to exist.